All right, this is Honors Algebra 2 Pre-Calc. We're doing section 7.2 in Algebra 2. This is our third video. We're going to do a quick video on continuity of a polynomial. So continuity of a polynomial, every polynomial function, y equals p of x, is continuous for all values of x. Right now, that probably doesn't mean much. Later in Algebra 2, in Chapter 8, we're going to learn a lot more about the ways that a function can be discontinuous. In AP/AB Calc, and also again in AP/BC Calc, we'll use the mathy definition of continuity. But here, all we're going to say is that continuity means that you can draw the curve without picking up your pen. So polynomials are super happy, nice, convenient functions that are always continuous, which is helpful as we move forward in math. As you get to calculus, you don't even have to justify that a polynomial is continuous. You can just say, hey, that's a polynomial, and we all know that it means it's continuous. Just want to give you a quick visual of what I mean by continuous versus discontinuous. So here are some examples of continuous functions, right? So here's a terrible version of, let's say, x squared or something akin to that, right? Nice, happy. I did pick up my pen to draw the arrow, but you get the gist. That doesn't count. That's a nice, happy, continuous function. I could have a function that looks like this. That's a nice, happy, continuous function, right? I could even have a function like a square root function that starts here and then goes like this, and it doesn't exist for all x values, but it is definitely continuous everywhere that it exists, okay? Those are examples of continuous functions. Here are some examples of functions with discontinuities. Sometimes we get curves that have what's called a vertical asymptote, right? So a vertical asymptote on its own doesn't necessarily make something discontinuous. In fact, if I put another continuous function up here, we learned about the log function, right? This is a log function. Right? Let's just call this y equals the natural log of x. It also has a vertical asymptote, but it's continuous because it's only got the one side. What makes this a function that has a discontinuity is that there are two branches, one on either side of the asymptote. And I can't draw it without lifting up my pen because I draw this piece and I draw this piece. Well, there's no way to get from here to here without lifting up my pen. So that's an example of a discontinuity. Another kind of discontinuity is what we call a jump discontinuity. So maybe I have a graph that looks like this, and then down here looks like this. We saw that a lot with piecewise functions, right? This is an example of a discontinuity. There's no way I can draw that section of the graph. So just like this vertical asymptote was a discontinuity, this jump would be a discontinuity. And then another one is what we call a hole, right? And they look like this. And I know there's always somebody who argues, oh, hey, Hogan, you could just awkwardly draw around the circle a couple times and then not pick up your pen. But that's not the intent behind the phrase that you don't have to pick up your pen. So this is an example of a jump. This is an example of what's called a vertical asymptote. And this was an example of a hole. And all of those are examples of discontinuities. So again, the purpose of this video is just to point out that polynomials, nice, happy polynomial functions, always fall in this top category of continuous functions, are never discontinuous. And we'll do a lot more with discontinuities later. But a lot of the theorems that we learn in calculus, a lot of the things that we use in calculus only apply to continuous functions, which means polynomials being continuous is a pretty important concept. So that's it for this video.